Hello Year 12 and welcome to a video on the first part of our overview of topic 9, looking at the features of 9A, B and C. Now with this topic the whole thing is about the idea of something that's normally distributed. And so we get, in each question we get clues as to how to fill this in and how to do these answers here. Let's have a look at what clues give us in the question. Firstly, we've got how long. So how long a battle royale match lasts in popular computer game known as Fortnite. So we're dealing with minutes. Now with a normal distribution, that's data, so it can be anything that we can get information about. So data this time is about how long something goes for, and in this case it's the Fortnite game. Alright, now we've got an average. Next clue is average, which is the same as the mean, and that lasts 20 minutes. So straight away on this distribution here, our normal distribution, the mean always goes in the middle, so that will be 20. Always the mean goes right there in the middle. And we've got a standard deviation, which is the measure of the spread of 5 minutes. Can be, if the standard deviation was longer, then what I'm about to do would change a bit. But we've got 5 minutes as a standard deviation, and that means for each one of these dotted lines, that represents 5 minutes time. So the next division is at 25. Going back this way, we're down to 15, 25 to 30, 30 to 35. 15 goes to 10, and then down to 5. So that's the first thing we do. We fill in the divisions for each one of these dotted lines, which represents one standard deviation. Now, as you can see, most of the games last in the middle here, around 15 to 25 somewhere, and as you go longer in time, the number of games is less and less, and so the same with less in time. So there's not really many above 35 minutes and not really many below 5. Now exactly how many depends on the way the normal distribution spreads the marks or the scores, and for each one of these graphs the percent is the same. So between one standard deviation below and one above, each one of these is 34%. So 34% of the games played last between 20 and 25 minutes, 34% between 15 and 20 minutes. The next one, going from 25 to 30, is only 13.5%. And the same on this side. Between 10 and 15 minutes, only 13.5% of the games played. Over here, let's do a little arrow, it's hard to fit. And in 30 to 35 minutes, only 2.35% of the games played last between 30 and 35 minutes. Same down here, between 5 and 10 minutes. 2.35%. Now we didn't be able to fit it on the graph here, but down here in these extremes, the lowest extreme is 0.15%, and the same up here above 35 is 0.15%. So there's our percents, and they're the same for each normal distribution. Between each standard deviation you're going to get the same percent. From here to there, that's the first standard deviation, 34%. The second one, 13.5%. The third one, 2.35, and the same going the other way. Oh, knowing all that, let's have a look if we can fill out these questions. Percentage of, now that we know the percents, these are easy. What percentage of matches last between 15 and 25 minutes? There's our 15-minute mark and our 25-minute mark, and we just add up those 2%, makes it 68%. Percent of matches last between 10 and 30 minutes. 10 to 30, that's a bit broader. We've got our 68% in the middle, plus these two, 13.5 and 13.5 adds up to 27. So 68 plus 27 equals 95%. 95% of the games last between 10 and 30 minutes. What percent of matches last longer than 25 minutes? Longer than 25 are these 3%. 13.5, 2.35, 0.15. So we just plus 2.35 plus 0.15. That adds up to 2.5, 16%. Only 16% of the matches last longer than 25 minutes. What about less than 20? Well, 20 is our halfway point, and everything to this side of 20 is less than 20, and that's 50% of the games last less than 20. Half of the games. What percentage of the matches last less than 5 minutes? That's that little percent here, only a tiny percent, 0.15%. If I played 120 matches, how many of those matches last longer than 30? So lasting longer than 30 is everything from here up, and we add up these 2%, we get 2.5% of the games last longer than 30. Now if we want to find out how many out of 120, we do this. So let me just see if I can get the calculator up and running. What was our 2.5%? 2.5% times 120, only 3. If I played 120 matches, only 3 would last longer than 30 minutes. Okay, next step. Different mean and standard deviation. For a different example, this one's our HSC standard maths. And this is fact that the marks are normally distributed. So we've got to look at it like this. The average mark was 60%. So straight away, 60%. That's our mean, average. And this time, standard deviation of 12. So not dealing with minutes this time, we're dealing with marks. So from this one to this first division, one standard deviation is 12 more than that. We go to 72, and then the next one is 84, and finally up to 96. Remember that in each division, it's the same percents each time. Going back this way, 12 less than 60 is 48. Then we go down to 36, and then down to 24. So there's the standard deviations. One standard deviation, 60 to 72. Next one is 72 to 84, and 84 to 96. And we're going to refer back to the percents to see if we can answer these questions. What percent of students receive a mark above 96? That was our final extreme one, which was 0.15%. Percentage of students receive a mark between 24 and 84. So there's this one, this one, this one, this one, and this one. There's 5 of them. Starting with this one was 2.35, plus the next division was 13.5. I'm just going by these percents here, 2.35, 13.5, then 68, oops, wrong one, plus 68, 2.35, 13.5, 34, 34, and lastly is the next 13.5 one. I think that's right. 24 and 84. 24, 84. Yep, they're the percents. Just remember, always doing with these same percents each time. 2.35, yep, that's all good. So let's see if we can add those up. Okay, plus the 68, and another 13.5. I think that's it. 97.35%. There we go. Last one. 30,160 students complete the examination. How many students receive a mark less than 36? Well, 36, that's our 1.35% for this last bit. And 0.15, that should be 2.35. Yep, plus 0.15 equals 2.5%. Remember that within each of these dotted lines, the percent, even though the mean and the standard deviation is different, the percent stays the same for every single question. So we've got last two divisions are 2.35 and 0.15. Okay, so that's a percent. So to get the answer, let's get it right, 2.5% is the percentage times how many people? 30,160. What's that give us? Times 30,160. Only 754 equals 754. Answer. Okay, there's our answer for that page. Next, Z-scores. Okay, so what Z-scores are good for? And there's a very important part of this topic. Basically, if you got did a test and you got a score of 35% in one test, and then in another test you got 63%, you'd automatically think, well, I did better than this one because I passed. What Z-scores do is have a true comparison, because you compare your score with the average. That's basically what Z-scores do. Compare your score with the average. So this might have been a really, really hard test, and that might have been a really, really easy one. So what Z-scores do is help us compare one test to another one. And here is a formula to work out the Z-score. And just remember, that's a score that compares your score with the average. So let's see what this means. Now, we've got two examples. We've got three examples. So to find the Z-score, let's see what the first one says. Z-score for someone who, we've got people spend time in the shower. is normally distributed and the average time is 10 minutes with a standard deviation of 3. Well, let's firstly get what this means compared to this. So X is your score. The raw score, the original score, X with a bar on top, is the mean or average. Average. And S is the standard deviation, the spread. Basically that means the higher the standard deviation, the further the marks are spread over, above and below the mean. So what's that mean for this one here? So if you had a standard deviation of 1 with people sharing for 10 minutes, the variation from 10 minutes higher and lower would be not very wide. But we've only got a standard deviation of 3. So let's do this. Z equals the original score. Well, let's see. This person spends 16 minutes in the shower. That's our X. So I'll put 16 here. 16 first. That's their score. That's how long they spent in the shower. Then we subtract from that the mean, which it says here the average time is 10, over the standard deviation is 3. Now 16 minus 10 is 6 over 3. Z score, you can simplify that to 2. That's our Z score for this one. So he'd be sitting in here somewhere. Z score, no, 2 this side. 10 minutes, 13, 16, he'll be up here on the upper end. Okay. Average height of a male is 176, so already we've got X bar. Average mean is 176. Normally distributed, so we're dealing with this curve, standard deviation of 10, so S equals 10. And Michael Jordan is 198 centimetres, so his score is 198. What's his Z score? Okay, same formula. His score, 198. Take away the X bar average, 176. Over the standard deviation, which is 10. Now that equals, what's that? 198 minus 176, that's 22. Over 10 equals 2.2 is Michael Jordan's Z score. Okay, Muggsy Bogues, shortest NBA player ever at 160. What's his Z score? Well, we've got the same X bar. And the same standard deviation. 10, but his score is 160. That's how tall he is. So the Z score for him is his score, the X, minus the X bar average mean, which is 176, over standard deviation, which is still 10. Now that is going to be a minus number, minus 16 over 10 equals minus 1.6. That's his Z score. So Z score here of 0, 1, 2, 3, minus 1, minus 2, minus 3. Michael Jordan is 2.2 up here somewhere. That's his Z score. And Muggsy Bogues minus 1.6 is down here. And that's it. Thank you very much.